Alright, hello everyone. So today I'm going to work through the Year 12 Y13 integration graph sketching paper for the KLSMC2025. And in this video, I'm going to focus on the integration part only, right? So if you're interested in the graph sketching, you can just plot in Desmos and just see how the graph looks like. So I'm not going to talk much about it. So let's get started on our questions. Right. So our first question is to evaluate the integral, the integration of x to the x cubed times cos x from negative pi to pi. So for this function, we have to realize that this, if we call this f of x, it follows the property that f of negative x equals to the negative of f of x. And let me show you why. So if we consider a function, right, f of that has the property of f of negative x equals to negative f of x, it will look something like this. Right, this is an example of the function, right? Like the negative x part, so like here is literally just an inverted of the positive part along the x, about the x-axis. And it is quite evident that if we decompose this function so that we call x to the power of x cubed, if we call this h of x, and if we call cosine x g of x, so our function is f of x equals to h of x times g of x. So then what you will get is that if you consider the graph for x cubed, it looks something like this. And it's quite clear that it should be an odd function, because x to the power of q, if we consider negative x to the power of q, it essentially equals to negative x cubed, right? So it follows the property that f of negative x equals to negative of f of x, right? So then, because x cubed follows this property, we call x cubed, which is our h of x, we call our h of x to be odd. Okay, so h of x is odd. Now let's consider the function g of x equals to cos x. And if you consider the graph, it looks something like this, right? And it's symmetric about the y-axis without changing the sign, without actually flipping the sign. So cosine x actually follows a property where if g of x is cosine x, then cosine negative x is actually equals to cosine x. So g of negative x is equals to g of x. So, and we define function with these properties to be an even function. So we say g of x is an even function. Okay. But now think about this. What happens if you multiply an even function with an odd function? What function would it be? So let's consider f of negative x equals to h of negative x times g of negative x. And we know that because h of x is odd, so h of negative x equals to negative of h of x. And g of negative x, because g of x is even, it's essentially the same as g of x. So f of negative x, we can simplify into negative of times h of x times g of x, which is essentially just negative f of x. So we proved that if one of our functions, so f of x equals to h of x, g of x, if h of x is odd and g of x is even, then we know the function for f of x must be odd as well, because it follows this property that f of negative x equals to negative of f of x. We just derived it. And now it is pretty evident how can we solve this question. So because f of negative x equals to negative f of x, the graph must look something like that's terrible drawing. So it might look something like this, so that if I integrate from negative pi to pi, because right, if we flip our signs for x, the y value also flipped. So in fact, the area will cancel out. So basically, the result of this integral will therefore be 0. All right. Let's see question 2. So Zicheng's favorite function, yep, that's me. Z of x is an even function. f of x is f of x is said to be even if f of x equals to f of negative x for all values of x, and we're given these two properties. Okay, so recall the definition of even function. It is basically set to f of x equals to f of negative x. So this means that our function is symmetric about the y-axis, right? So for example, this is an example of an even function, right? Symmetric about the y-axis, and it should be self-evident that if you find the area from -1 to 0, and then find the area from 0 to 1, and because it's symmetric, the two areas should be the same, right? So therefore, f of 0 to 1 z of x dx should be equal to equal to the integration of z of x from -1 to 0. Yeah, so these two should be equivalent to another. Okay, so how do we find this? Well, because we know it's an even function, we can decompose this. So we can decompose this into the integration from 1 to 0 z of x with respect to x plus the integration of z of x with respect to x from 0 to -1. So this is equivalent as this, right? So this equals to integration of z of x with respect to x from 1 to -1 z of x, and we know this equals to pi. And because it's an even function, these two should be the same. So we know that integration from 1, 0, z of x plus integration of z of x with respect to x from 0 to -1. So sorry, these two are supposed to be equal to another, and they will basically just split this pi into equal parts. So they both will equal to pi over 2. So pi over 2 plus pi over 2 gives us this pi, right? Okay. And for this, it should be quite self-evident that because it's an even function, right? So then -2, the integration of our function from -2 to 0 equals to the integration of our function from 0 to 2, and they will split this 2e squared into halves. So each term will equals to e squared. So if we add them together to make this, it will give us 2e squared, right? Okay. Now, how do we evaluate this? Well, we can divide that integral into parts. So the integration of our function from -1 to 2 can be written as the integration of our function from -1 to 0 plus the integration of our function from 0 to 2, right? And of course, we already know this. This is just e squared, right? This is just this e squared terms. But how do we find this? We know the integration of from 0 to -1, but we want the integration from -1 to 0. Well, think of what integration from 0 to -1 means. It basically means we're doing the integration in the negative x direction. So for example, this is our function. This is 0, this is -1. We're basically integrating in this direction, right? So our delta x increment will be negative, so we will get a negative area. But if we integrate from -1 to 0, our delta x increment will be positive, so we get positive area. So in fact, that the integration from -1 to 0 z of x dx is basically just the negative of our function of our integration of the same function from 0 to -1. So we know this will basically just be the negative of this. So this is negative pi over 2. So combining these two terms give us e squared minus pi over 2, and this will be our final answer. Okay. Problem 3. So find the value of f of ln 10 when function f of x satisfies the equation f of x equals to e to the power of x plus the integration of f of t from integrated from 0 to 1. So how do we do that? Well, let's lay out our function. So f of x equals to e to the power of x plus integration from 0 to 1. Is it 0 to 1? Yep, 0 to 1. T f of t dt. Now, first of all, let's guess a form for our function f of x. And let me ask you guys a question first. Does this term depend on x or not? Well, the answer is don't, because you don't see an x in the integrand, nor in the boundaries, right? This term is completely irrelevant of x. So we know that because our function is a function that's dependent on x, right? And we know that this term doesn't depend on x. So basically, we can rewrite our function as e to the power of x plus a constant that is independent of x. So we know how does the general function, the form the general function should take. And now let's try to evaluate the constant c, so then we can substitute our value back. So okay, all right. So what we can do is so basically f of t will just be e to the power of t plus c, because we're merely just replacing x with t, and then we can start evaluating the integral. So f of x equals to e to the power of x plus integration from 0 to 1 t times e to the power of t plus c. Okay. To evaluate in this integral, it's a bit complicated, but not that complicated. So e to the power of x. So we need to consider an integration by parts here. So let's first divide the integration into two parts. T e to the power of t dt plus ct dt. And we know that this part is very straightforward. So I'm gonna evaluate this first. So this will be, so our f of x will be equals to e to the power of x plus, and recall the formula for integration by part. Yup, we're going to use this identity. So so f of x equals to e to the power of x plus e to the power of t from 1 to 0, because I'm setting my t to be, it's t times e to the power of t minus 0 1 e to the power of t dt plus integration from 0 1 ct dt. So it's e to the power of x, and we know this one is just plus e to the power of 1. Yep. Minus et 1 0 plus plus 1 over 2 times c times t squared from 1 0. So just do e to the power of x plus e to the power of 1 minus e to the power of 1 plus e to the power of 0, which is just 1 plus half c. So that is our function. And now what we do is that the equivalent, because we write our function as f of x equals to e to the power of xc, and when we integrate it, right, we know this reduced to a form of our function is also in the form of e to the power of x plus half c plus 1. So now what we do is that we equivalent these two terms, right? We say these two terms to be, these two terms to be equal. So we're given the condition c equals to half c plus 1. And rearranging this will basically give us c equals to 2, right? So our function is therefore f of x equals to e to the power of x plus 2. And so now let's substitute the value when x equals to ln 10. So f of ln 10 is basically just 10 plus 2, which is 12. So we got our final answer, 12. Okay, let's do problem 4. So the area bounded by x-axis, y-axis, and the curve y equals to the square root of 9 minus x minus 2, and we wish to find the value of 6x. So let's set the thing out. So if you consider the graph, it looks something like this, right? It looks something like this, and we want to find this area. So what you do is that you just integrate you find when this curve intersects with the x-axis. So that will be 0 equals to 9 minus x minus 2. So root 9 minus x equals to 2. So 9 minus x is 4, and therefore x equals to 5. Okay. So now what we then do is we just integrate this from 0 to 5. So integration of our function from 0 to 5. Our function is 9 minus root of 9 minus x minus 2. So this is s. That's 5. So to integrate this function, you can consider a substitution, but I don't think that's needed because it should be a very straightforward integration where you can hopefully realize that this goes to a form of 9 minus x to the power of 2 over 3 times negative, this is to the power of 3 over 2, and the constant in front should be the negative 2 over 3. So that 3 over 2 times negative 2 over 3 times this negative 1 factor will give us 1. So it will give us, like, if we differentiate this, it will basically give us root 9 minus x again. Okay. And negative 2 obviously just integrates to negative 2x. Yeah. So let's substitute our boundaries in. So it will be equals to negative 2 over 3 times 9 minus 5, which is 4 to the power of 3 over 2, minus 2 to the power of minus 2 times 5, okay, minus negative 2 over 3 times 9, because we're substituting x equals to 0, and this 2x term is just 0, but this negative 2 over 3 times 9 minus x to the power of 3 over 2 term is just, the x is 0, so it's just 9 in the, yep. So if you simplify this, you will basically just get negative 16 over 3 minus 10 plus 18, which is 8 over 3. And because we want the value of 6x, so we just times this by 6. So 6x equals to 6 times 8 over 3, which is 16. So our final answer is therefore 16. Now we're on to question 5. So now question 5, you can do there's two ways of doing it. So the first way is definitely by considering this important thing, that f of x plus 2 is equals to f of x, and that with this you can basically note, because the function is periodic, so the integration from 0 to 1 the integration from 0 to 2 f of x dx should be same to the integration of f of x from 2 to 4. Should be also the same from 4 to 6. And that's because our function is periodic as we moved 2 units from our x-axis, right? So that's one way of approaching this question, but there's a trick to solve this question easily. So think of a function that follows these two properties. Well, let's think of this. F of x equals to a constant. These two properties definitely hold, right? It definitely holds. It's periodic as we move the units of 2, and it's an even function, right? So it's like a very trivial function. So what we then can do is that we find a particularly constant that this thing evaluates to 15. So therefore, the integration of 2cx plus 3c from negative 1 to 1 equals to 15. So it will give us cx squared plus 3cx from 1 to -1 should give us 15. So c plus 3c plus minus c minus 3c should give us 15. So 6c equals to 15. So c should be equals to 15 over 6. Right. And now we want our integration from -6 to 10. So hold on, just give me a second. Sorry. C minus 3c 2x plus 3c. So f of x equals to 15 over 6. The integration from -6 to 10. So we're essentially just finding 15 over 6. So equals to 15 over 6 times 10 plus 6 equals to 15 over 6 times 16. Wait, hold on. I might have done something wrong. No, yeah. So 15 over 6, it's going to be 5 over 2 times 16, which is just 40. Right. So this will be your final answer. So that's a trick of doing this question, is by realizing that f of x equals to a constant. So by realizing that if f of x equals to 5 over 2, it follows this property, right? It follows all these three properties, right? Then yeah, that's just, because it follows all these three properties, then let's just say f of x equals to 5 over 2. Yeah, that's it. This is how we approach this question. Right, problem 6. So problem 6 is slightly more complicated. I mean, not that complicated. So you have to notice that f of x is a quadratic function, and what you can do is that you just integrate it, right, many times, and you eventually you will have like an equation governing your coefficients for a quadratic. So f of x equals to ax squared plus bx plus c, and you also have this condition, so that basically means c must be equals to -1. So you can just do that, right? So sorry, but let us consider some stuff. Let's consider what this means. The integration from -1 to -1 equals to the integration from 0 to 1 equals to the integration from -1 to 0. So it's basically saying, and the most important part that I would say is this part, right? It says the integration of our quadratic from -1 to 0 is equals to our integration from 0 to 1. So from this, like if you visualize your quadratic graph, and for these two areas to be equal, so for these two integral results to be equal to another, you know that your quadratic must be symmetric about x equals to 0. So therefore we know that b is 0, because our quadratic must be symmetric to our y-axis, because that these two integrals are equal. So these two are equal, so we know that it must be symmetric against the y-axis. So we know b equals to 0. So now we only need to find a, right? So we reduced our function to f of x equals to ax squared minus 1. Okay. And to find a, what we can do is we integration from so you can consider a trivial case, right? If all these things, I mean, it's not a trivial case. If these equals to this, so 1, -1, f of x dx is definitely equals to the sum of these two integrals, right? And you know that these must be equal to another. Like these three terms must equal, so then it must be that 0 equals to 0 plus 0. This is so this will only hold true, and given the extra condition that these three terms are equal, then we know that each term must be equals to 0, right? So what you can do is that you basically solve this equation. So you know that one term must be 0, so let's just consider this term. So the integration of ax squared minus 1 from 0 to 1 must be equals to 0. So therefore, 1/3 of ax cubed minus x from evaluate from 1 to 0 must be equals to 0. So 1/3a minus 1 will be 0. So a equals to 3. So our function is basically f of x equals to 3x squared minus 1. Substituting the value for f of 2, it's essentially just f of 2 will be 12 minus 1, so equals to 11. So 11 is our final answer. Right, problem 7. Given n and m are non-zero integers, which is the most general condition such that the expression below holds true? So what you can do is that just by looking at this, I personally cannot find any ways of integrating it. I definitely need to do some manipulations with the integrand to a form that is easy or simple to integrate. But how can I do that? Right, let's consider this identity. Cosine a plus b, cosine a minus b minus cosine a plus b. What does this equals to? And if you refer to the formula sheet, you know that this is basically, this is cosine a cosine b plus sine a sine b, and this is basically just cosine a, let me just add a bracket. So cosine a cosine b minus sine a sine b. Right, so this will give us 2 sine a sine b. Right, and because our integral, so basically we can replace this with 0 to pi n minus m. Right, you can replace this with cosine m minus m x minus cosine m plus m x. Yeah, so basically, you replace this integrand with this, and this is definitely integrable. And I left the constant. I don't care about the constant too, because we need our integral to evaluate to 0. So this 2, if we have a constant in front, it cancels out, right? So only this part matters. So now let's try to integrate this. So this equals to, the first part equals to n minus m 1 over n minus m times sine n minus m x minus 1 over n plus m sine n plus m x integrated from 0 to pi. So and we need this to equals to 0. Now think about it. Because n minus m is definitely also an integer, because we are already given that n and m are non-zero integers. So n minus m or n plus m must also be integers. Okay? So, and we know that an integer, let's say an integer a times pi, this is definitely going to be 0. So is sine 0. It's also 0. So we know that these terms, when substituting our values for x equals to pi or x equals to 0, this will always give us 0, right? It will always give us 0. But there's a technical point here, is that we have a because we have a condition here, so that n must be not equals to, so n must be different from m, and n must be different from negative m, right? Because, or otherwise the integral will evaluate to a value that is how do you call that? So well, basically you'll find the numerator, the denominator to be non-zero value, right? No, you have the denominator to be 0, which just doesn't make sense anymore. So your general conditions is that is basically this. Sorry, I forgot to put and this as well. But like speaking of the most general ones, it's basically f, right? I mean, the most general condition will be m is not equals to n and m is not equals to negative n. But like, because since here we're considering yeah, sorry, this should be like a n and m are non-zero positive integers. I am sorry for that technical details. So yeah, but like, so this is basically how you would approach the question. All right. So now let's do problem 8. So our function is basically an integral from 0 to 1. One plus x cubed times 1 plus x squared. Right, so to evaluate this integral, we can try expanding it using partial fractions. How am I going to do that? So, well, I know that x cubed plus 1 can be factored to x plus 1 times x squared minus x plus 1. So this is essentially just, so we can represent our denominator as 1 plus x times 1 minus x plus x squared times 1 plus x squared. And we try expanding this in terms of the sum of partial fractions. So let's try to express this as this form: a over 1 plus x plus bx plus c, over 1 minus x plus x squared plus dx plus e over x squared plus 1. So this whole thing. Yes. So we know the denominator is 1 unless we do our partial fraction, so I'll just list it down. So we know we are given that ax squared minus x plus 1 times x squared plus 1 plus bx plus c x plus 1 right. A very quick way of finding one constant is that if we substitute a value for x equals to -1. So these two terms cancels out. So we only left with a times, because we're substituting x equals to -1. So -1, 1 plus 1. So it's 3 times 2 equals to 1. So we know that a must be 1 over 6. So that's a very trivial way of finding a. And now to find b, c, d, and e, it's going to be slightly more complicated. So we're going to compare the coefficients. We know the constant is 1, right? Because on the right hand side, its constant is 1. So, and the constant terms from the left hand side is is basically a plus c plus e. Right, so a plus c plus e must be equals to 1. Comparing the coefficients for the x, for the term x, we get negative a plus b plus c plus d equals to 0. For the coefficient of x squared, we get 2a plus b plus c equals to 0. For our coefficient for x cubed, we got negative a plus c plus b plus b plus e equals to 0. And x to the power of 4 have a plus b plus d to be 0. Right, so this is like basically comparing our coefficients. And since we already know a, we can consider, so let's say this is equation 1, equation 2, equation 3, equation 4, equation 5. Let us subtract equation 5 and equation 2. So what we get is 2a minus, so equation 5 minus equation 2 will give us 2a minus c equals to 0, so c is 2a. So therefore we know that c is going to be 1 over 3. Right. And then from equation 3, because we know a and c at the same time, so we can find b, right? So 2a plus b plus c equals to 0. So 1 over 3 plus b plus 1 over 3 equals to 1, so plus 1 over 3 equals to 0. So therefore b equals to negative 2 over 3. Right, so now we got b. And now let's look at equation 1. A plus c plus e equals to 1. So 1 over 6 plus 1 over 3 plus e equals to 1. So we know that e must be equals to 1 over 2. Right? E is 1 over 2. And by considering the last equation, a plus b plus d equals to 0, because we know a and b, so we can find d using the same way. So 1 over 6 minus 2 over 3 plus d equals to 0. So d is 1 over 2. So we get a equals to 1 over 6, b equals to negative 2 over 3, c equals to 1 over 3, d equals to 1 over 2, and e equals to 1 over 2. Okay. So we can, so basically now we rewrite our function, this to be equal to integration from the 1, substituting in our value. So it's going to be 1 over 6 over 1 plus x plus negative 2 over 3 x plus 1 over 3 over 1 minus x plus x squared plus half x plus half over 1 plus x squared dx. Okay. Right, so let's simplify this a bit. So this equals to 1 over 6 for our function plus negative 1 over 3. Sorry, so just do negative 1 over 3. And you know why I factor this in front. It's like it basically makes our integration easier to do. 2x, sorry, so it will be 2x minus 1. Yep. Plus 1 over 4. Right. So basically, I write this integrand, I divide it into its component, so that each integrand in each term is like it's more easier to integrate. Okay. So the first one is basically just sorry. So well, it's basically 1 over 6 ln 1 plus x minus 1 over 3 ln 1 minus x plus x squared plus 1 over 4 ln x to the x squared plus 1 plus 1 over 2 arc 10x. Right, so this is how we integrate this, right, and applying our boundaries from 0 to 1. So what you will do is that, so this will becomes 1 over 6 ln 2. I don't need that bracket. Yeah, 1 over 6 ln 2. 1 minus 1 plus 1 is 1. Ln of 1 is 0, so that term is gone. So then it will be plus 1 over 4 ln 2 because of this term. And arctan of 1 is pi over 4, so plus 1 over 2 times pi over 4. Minus, and if we substitute x equals to 0, all terms will be 0, so it's just 0, yeah. So this simplifies to 5 over 12 ln 2 plus pi over 8. And this is basically our final answer. Okay. Alright. By first applying a suitable substitution, determine the antiderivative of the integral below. So, I want you all to consider the substitution t equals to sine x minus cos x. Sine x minus cos x. And the good thing about this substitution is that you can hopefully realize that t prime, which is or dt over dx, is essentially our denominator. It's equals to sine x plus cos x, which is basically our denominator. Which is basically our numerator. So, yeah. So I want you all to consider this substitution. So therefore, we can replace our function to be, because we know that sine x plus cos x times dt. So then we can basically say that sine x plus cos x, or 1 minus sine x cos x dx, is basically the same as integration of 1 dt, right? Because sine x plus cos x is essentially our derivative of t, so we can just replace this with dt. Okay. So now let's try to express our denominator in terms of t. So recall t squared equals to sine squared plus cos squared minus 2 sine x cos x. Right, so t squared is equals to 1 minus 2 sine x cos x. Okay. So if we wish to express sine x cos x in terms of t, what we can do is we move t squared to the right, and so 2 sine x cos x equals to 1 minus t squared. So sine x cos x is 1 minus t squared over 2. Okay, so then we can do some changing and resubstitution. So we get 1 minus t squared 2 dt. Okay. And so this equals to this equals to integration of 1 over 2 plus 1 over 2 t squared dt, which is equals to 2 times integration of over 1 plus t squared dt. And you know that this is basically essentially equals to 2 arc tan t plus c. And if we replace t back, so equals to 2 times arc tan sine x. So basically we're just putting t back as. So this will be our final form for our answer. Okay. So now let's do problem 10. The shortest time for a particle to travel between 2 points can be modeled as the following. So what you will basically do is that you try to find dy dx. What is dy dx? Well, dy dx can be solved as dy d theta over dx d theta. Like a very rough idea will be like the theta's cancel out. So basically you find the differentiation of y with respect to theta over the differentiation of x with respect to theta, and the theta cancels out you only with dy dx. So that's a very rough idea, a very rough way of understanding how it works. So what is dy d theta? R is a constant though, so dy over d theta is basically just dy d theta is just r sine theta. And dx d theta would be r times 1 minus cos theta. Right, so dy dx would therefore be r sine theta over r times 1 minus cosine theta, which is essentially just sine theta over 1 minus cos theta. And then you can substitute in to this thing, so equals to integration from to b one plus this whole thing squared, so two g so 2g, and we wish to replace the r integration with respect to theta rather with respect to x, so we replace dx with dx d theta, right, and we change our boundaries accordingly, because we're moving from this point to this point, right? The time taken to move is, so you start with t equals to 0, then you end at t equals to 1, so it's just integrating from 0 to 1. And dx d theta is r times 1 minus cos theta. Okay, so it is therefore we can replace dx over d theta with r times 1 minus cos theta. And there will be some really nice simplifications going on there. So, okay. So what we then do is that we can expand some terms. So, if we put this 1 minus cos theta term inside of our square root, we will get something like 1 minus cos theta squared plus sine squared over 2gr times 1 minus cos theta integration of r, and yeah, d theta. So this 1 minus cos, so if we write our sine theta squared as y minus cosine theta squared, so we will get 1 minus cos theta plus 1 plus cos theta over 2gr. And if we put r inside our square root, we get integration of 2r squared over 2gr d theta. So it's just basically just, and this thing inside our square root simplifies into r over g. And this just integrates to root r over g. And that will be our final answer. Right, problem 11. It's a trick question. So what I want you to consider is integration of 0 to pi over 2. 1 over 1 plus cotangent to the x to the power of a dx. So recall the graph for our cotangent looks something like this. Sorry, it's a terrible drawing. Yep, it's so bad. And our tan looks something like this. Right. So it should be evident that actually this is equals to that, right? Because like you can think of this as like cotangent. It's basically like you're starting with like the positive infinity part. You slowly go down to 0, and the tan is basically the opposite to it. So these two should be equal to another. So if I call this the result of this integral I, then I is also equals to replacing the tan with cotangent. But now let's consider this. What is 1 plus? What is the sum of the two integrands? We can rewrite it as 1 over 1 plus 1 over 1 plus equals to and it should be quite evident that this is actually equals to 1. So therefore, we know that I plus I equals to 2I equals to the integration of pi over 2, 0, 1 over 1 plus 1 over, sorry, it's cotangent. So you know this is basically just integration of 1, which is just pi over 2. And because we know this is equals to this, right? It's 2i, right? So 2i equals to pi over 2. So I equals to pi over 4. So this integral basically just evaluates to pi over 4. And that will be our final answer. Right. Problem 12. So problem 12, it's a multivariable integration. So let us consider the region of space that we're integrating our functions. So our x is constrained between 1 over 3, and our y is constrained between like what seemingly looks a little bit more complicated, but it's not complicated. Trust me, it's not. So okay, what we then do is that we can start so like if we look at our xy plane, right, it's from 1 to 3, okay, and we think of this, the boundaries, y equals to half root 4x minus 3 minus x squared. So let us consider what does root 4x minus 3 minus x squared means. So it basically means that if y equals to root 4x minus 3 minus x squared, we can do some, I'm going to use black. So we can actually think this as x as 1 minus x minus 2 squared. You can confirm that it should be the same, right? So now if we rewrite it, we can write it as x minus 2 squared plus y squared equals to 1. So this looks much more sense, right? This is basically just like a circle with radius 1, center at 2. That's negative 1. That is 3. Okay. So that's basically a circle centered at 2. Sorry. That's 1. What am I saying? Sorry. And the circle will be of radius 1, right? But what does this 1 over 2 means? This is basically like our circle used to be like a normal circle with radius 1, right? Center at x equals to 2. What it does is I basically just squeeze it. You squeeze the y-axis, right? So this is you will get an ellipse-looking shape, right? This is so basically this is the area you will be integrating your function with. And obviously, you're not going to do some you're not going to integrate by substitution or integration by some other algebraic techniques. What you're going to do is you're going to consider this thing geometrically. So this is much more simple to think of. Z equals to 1 minus y squared minus x minus 2 squared. This is basically just a unit hemisphere centered at 2, 0, right? So 2 is your x value, 0 is your y value. It's just a unit hemisphere. A unit hemisphere is a hemisphere with radius 1 centered there. But what does this 4y squared mean? So 4y squared is basically means that we are applying a transformation of our y-axis by, so it's like it used to be y squared here. Now we're considering like 2y squared. So it's basically you can think of like you're compressing your y-axis by a factor of 2. Right, so it's just like how we did this, right? It was like it used to be a circle with radius 1. You stretch the y direction, you compress it, right, by a factor of 2, you get something like this. So that's an ellipse shape. So like because you're only changing the y-axis, you're keeping your x-axis and z-axis unchanged, right? So your xz plane remain fixed. You're merely changing your y-axis. You're only changing one axis. So basically, your volume, as you do the transformation of your y-axis, your volume gets scaled the same factor. So your y-axis, it gets scaled by 1/2, right? Everything gets scaled by 1/2. So your volume will also get scaled by 1/2. So like, recall, how do you find the volume of this unit sphere for this stuff? It's just 2 over 3 times pi r squared, and your r is 1, so the volume would just be 2 over 3 pi. And because we're compressing the y-axis, we're replacing our y here with 2y. We're compressing our y-axis by a factor of 2, so we'll just divide this volume by 2. So v will just then be 1 over 3 pi. So this will be the value, the result of your integration. It's just 1 over 3 pi. Okay. Now let's think about problem 13. Problem 13, it's another multivariable integration question, and it's basically integrating of the floor function of x plus y. And I'm not going to talk to you about floor function. You can just read it, right? It literally explains what floor function is right here. So let us consider what value will our integrand take. So our x, let us consider the space that we are integrating. So it's like, so it's integrating of x from 0 to, sorry, it's a terrible drawing here. So it's so our x takes between 0 to 1, and our y takes between 0 to 2. Okay. And so the floor function can be basically sort of equals to, so if for our floor function equals to 0, then the x plus y must be bounded between 0 and 1, right? For our floor function to be 0. So this is just the shape of y is 1, y is less than 1 minus x. So the function will look something like this, right? So this is the part where our this is the part where this is the space where the floor function of x plus y equals to 0. Okay, and now let's consider when our floor function equals to 1. So it will equals to 1 given that x plus y is bounded between 1 and 2. So then basically we have this y is less than 2 minus x, and y with given and x is greater than or equals to 1 minus x at the same time. So this is basically the space for x plus y equals to 1. And by same reasoning, it should not be hard to identify that this is the part where x plus y, the floor function of x plus y equals to 2. Now you might argue that at the point 1, 2 in my xy plane, the value of the floor function equals to 3. But that's very trivial because only in this point of our integration of our the plane we're integrating, only that single point will get us a floor function of 3. So which is very trivial, right? So we don't care about that. So we only so basically we separated our integration space into these 3 separate parts. So this is 0, this is 1, this is 2. And recall integration. So because basically now we're literally separating this integration as like a discrete sum. So the area for this triangle is just 1 times 1 over 2. Yeah, for this triangle. And the floor function evaluates 0. So 1 plus 1 over 2 times 0. Plus the area for this parallelogram is going to be 1 times 1. And because our function evaluates to 1 there, 1 times 1 times 1. Plus the area for this triangle is 1 plus 1 over 2 times 2. Sorry, yeah, times 2, because 2, our floor function equals to 2 in this area. So it will just be equals to 1 plus 1. So our integral evaluates to 2. So that's it for the integration paper. I hope you enjoyed, and I hope it's a useful resource to practice for KLSMC 2026 and onwards. And thank you for watching.